Today we're going to talk about arithmetic sequences. A sequence is an ordered list of numbers. Each number in the sequence is called a term. Each term, an, has a specific position n in the sequence. So if you just look at this picture real quick, we can kind of see here, this would be a sequence of numbers going up. You can definitely see a pattern here, which we're going to talk more about in a few minutes. So this nth position tells us where in the sequence our number is. So 5 would be the first position, 10 second, third position would be here, and then the nth position is just going on as far as we would like it to go. In an arithmetic sequence, the difference between each pair of consecutive terms is exactly the same. So in the first example, we see 5. You would add 5 to get to 10, you would add 5 to get to 15, you'd add 5 to get 20, etc. This difference is called the common difference, which makes sense because it's the same number, so it's common over and over and over again. And each term is found by adding that common difference to the previous term. So notice the word difference. We're basically trying to find if we subtract the newest number from the oldest number to get that common difference. So we want to be looking for the number that we are adding each time to get to the next one. So let's look at a few examples. So in this example, we're just asked to extend the arithmetic sequence we see. So you can see that we are going from -7, we're subtracting 7 to get to -14, we're subtracting 7 to get to -21, we're subtracting -7 to get to -28, which would mean the next three terms would be -35, -42, and -49. So graphing one of these, so to graph one of these sequences, we're going to let the position, that n, in the sequence be our x value. And then the term, the number that's the term at that position, will be the y value. And we're going to plot those ordered pairs. So in this case, instead of x, y, it'd be n, comma, an. But really, it's the input is going to be our position. The output, which would be the y, will be what that number is in the sequence. So let's look at the sequence below, and we're going to talk about graphing it. So if I first make my x and y table, I have 4 points that we're going to be plotting. First position, the y is a 4. The second position, the y is an 8. Third position, it is 12. And the fourth position, it's at 16. So there's my table that I can now go ahead and graph. So I'm going to set up my graph with just the first quadrant because we only would see, in this case, positive positions going forward. So I've noticed that my scale, I've skipped a block each time on the x-axis to get 1, 2, 3, and 4 a little bit spaced out so it's not like crunched on each selves. For the y scale, I just went up by 2s. So I just, again, to try to not make it too messy, I kind of skipped over each of the blocks to get 4, 8, 12, and 16. And then simply it's just a matter of putting in our points. And there are my 4 points. Now, when you think about a sequence and you think about our graphs, a lot of times we would then grab a ruler and we would connect these dots and make a straight line. But in a sequence, this would be a discrete sequence. The domain is discrete. I'm not looking at position 1.5. There is no such thing as a position 2 1/3. So this would be my graph. I would not connect the dots for the arithmetic sequence. I would just plot the points, and the points from the table will go onto the graph. There is no line going through it. It is not a continuous domain. This would be a discrete domain. So our next example is to look at this graph to the right and to decide, is it an arithmetic sequence? So how would I know? So the reason I would know this is because if we think about a common difference of point to point to point, it would have a straight line look to it. Just like the graph we just made, it makes a perfect straight line, which is basically another way of saying it has a slope. And if it has a constant rate of change or slope, then we would be able to say that it is a arithmetic sequence from the graph. So just looking at a few of these points and calculating what the difference of our slopes would be, we can see that it is or it isn't. So from going from the first point to the second point, I'm seeing 15 down to 12 as my numerator for my change in y's over my change in x. And for my denominators, we went forward from 1 to 2, but remember we're subtracting, right? So I would get 3 over a negative 1, which equals negative 3. So the slope between those first 2 points is a negative 3. So then we would want to just verify that through several of the other points. And again, I would come down 3 and forward 1. That would also be a negative 3 slope. And lastly, from this one to this one, the 9 came down to 6, and then also a negative 1 in my denominator. So we see a negative 3 slope. So this would definitely be an arithmetic sequence. And again, remembering the sequence, the first position would be the 15, second position would be the 12, third position would be the 9, and the fourth position would be the 6. So there's a common difference of a minus 3. So yes, this would be an arithmetic sequence for those reasons. So because the terms of these arithmetic sequences have that common difference, the sequence has a constant rate of change, or m, which we know stands for slope. So the points represented would always lie in a straight line. So we can use the first term of the sequence and the common difference to write a linear function that describes that sequence. So here's the way this chart kind of builds this. It kind of shows how we can see how position 1 would be our first term. Then for position 2, notice what we did in the terms was we just added the common difference. For term 3, what we did was we added 2 of the common differences. So notice how over here, this would be kind of where this formula is starting to be built. 1 of the common differences, 2 of the common differences added to the first one gets the next sequence. Then the fourth one would be adding 3. So notice the fourth term has 3 common differences being added. So then you come all the way down to this, and this is where we see the formula really start to become developed. At the nth position, notice that all of the multiplied numbers by the d are 1 from the number you actually wanted. So this one was 3 for the fourth term. This was 2 for the third term. This is really 1 for the second term. So it's always the place that it's in minus 1 times d. So this is where the formula comes from. So let's just look a little bit further down to see how it actually looks. So here how this is the development of that sequence equation. So an is equal to a1 plus, in parentheses, n minus 1 d. So all those things basically are meaning. So the first term is the a1. N is the position of the term that you're looking for. D is the common difference. And the value of the position that you're looking for is that a sub n. So let's just do an example so you can see how that plays out. So here we are given the sequence, 14, 11, 8, and 5. And we want to first write the equation for the nth term of that sequence, meaning if we just kept going, we could figure out what that formula looks like or equation looks like. So we first want to see, number 1, that we can find the common difference. Hopefully we can see the common difference. We always want to think, what is the number we're adding here? So we're really adding negative 3 over and over and over again. So we're adding a negative 3. So our common difference is negative 3. So what's going to happen here is we're going to see a sub n. Our first term in the sequence is this 14. Then we would be adding the n minus 1. And then our common difference, hopefully we can see, is a negative 3. So the d, or the difference, is a negative 3. So we're subtracting 3 each time. It's not a 3, it is the negative 3 because it's what we are adding to each of the terms. So this is not really simplified. We want to think about simplifying this the best we can. So we think about our distributive property. We would get a to the nth, and then we would have 14. Then if I kind of did my distributive property backwards, I would get minus 3n and plus 3, because the negative 3 times a negative 1. And then I can simplify a little bit better on that right-hand side. And I'm also going to move my numbers in terms a little bit so that I get the n's in front. So I would end up with negative 3n plus 17. And that would be the equation that we would be using to find whatever term we would like to find in this sequence. So then it says to find a sub 50. Well, if you think about it, a sub 50, put it up here a little bit. This is, again, a notation. This is where the n becomes the 50, because that's the 50th term we want. We could certainly keep subtracting 3, 3, 3, 3, all the way to 50th term. Or now I can use my equation. And now that I have this equation, I'm going to plug in my n as a 50. And then I just solve. So I get a sub 50 is negative 50 plus 17 is negative 133. So if I was to continually go all the way to the end and just keep subtracting 3's over and over and over again, the 50th term would be negative 133. So we can also rewrite these equations of the arithmetic sequence with that a1 in common difference with the function notation. Because basically, as you just saw, we kind of wrote that in slope-intercept form, except that we have that a sub n, and we had an n instead of an x value. So basically, really what we're saying is we can certainly just rethink this as not a sub n, but now the function f of n, or you could even just think y equals mx plus b once we've solved it all the way down. So we're just going to kind of show one example of that. Basically the same idea. Really what we're replacing is the f of n instead of the a sub n. So here we have the bidding for a purse is increasing by $5 each bid after that initial bid of 60. So it looks like a table. It's also kind of still like an arithmetic sequence as we look through the table. Hopefully we can all notice that we are seeing a plus $5 for each purse that we are selling. So clearly we can see something that we've seen before as far as a slope or a linear table going. So to write this function, so because they're calling it this function, we're not going to use the a sub n, we're just going to call it f of n, since n is our variable for the arithmetic sequence. And here you can see that I plugged in the formula. So f of n equals 60, which is my initial amount to bid, plus that is my first in the sequence. Then we have plus n minus 1, which we always have. And then the common difference in this case is a positive 5. Now on the previous one we had a negative 3 because it was going down. Notice this one is going up. So it's the common difference is what's the number we're adding to the previous terms. We're adding a positive 5. And then again, to clear this up a little bit better, we do want to kind of turn this into a neater, easier to read formula. So again, if I use my distributive property, it's a little bit of a backwards way to do it because we usually have the number on the front, but we would get 5n minus 5. And then again, because we want to think of this as a slope-intercept look, and we end up with f of n equals 5n plus 55. So that would be the function that we'd be graphing on the graph paper to the left. So I'm just going to go ahead and do that. So I've kind of made my x and y axes. Again, this would only be in the positive quadrant 1 in this case because our numbers are going up on the positive side, and we wouldn't have negative positions of our bids. It's either 1 bid, 2 bid, 3 bid, 4 bid, etc. So to plot these points, notice on my y-axis, I have that little break thing again, simply because I didn't want to really have to go 0, 10, 20, 30, 40, 50, 60. Remember, this little break allows me to jump up to 60, but then I do need to have a consistent one going forward, and I decided to go with a positive 5, which hopefully makes sense. And then I just need to plot my points to make sure I can see what this graph is going to look like. So at the first bid, we have a 60, second bid, 65, third is at 70, and fourth is at 75. And again, notice I'm not going to connect these dots. This is not a continuous domain. It's a discrete domain because I either have 1 bid or 2 bids or 3 bids. I don't have any in-between number of bids. So that would be the graph. And this last one, we just got to think about our wording. So the winning bid is $105. How many bids were there? So again, we got to look at our equation and not just always jump to plugging in the n and solving for the y or the f of n in this case. So if the winning bid is dollars, the dollars is our y or output value, which means when I plug this in to solve this, I am going to start with the 105 in place of the f of n. And then I'm going to be solving for the number of bids. And remember, the number of bids in our case this time is the n. Then it's just a matter of finishing off our equation. So we know that means to subtract 55 from both sides to get 5n equals 50. And then when we divide by 5 on both sides, n equals 10. And then we want to include its 10 bids. That would get me to the 105. So I hope this makes some sense. The arithmetic sequences really create these linear relationships. And if we use that formula correctly, the a1 plus n minus 1 in parentheses times our common difference, or d, we can come up with the equations of these sequences to help be able to find future number in the line that we're looking for, whether it's the 50th term, the 100th term, the 1000th term of whatever sequence we're looking at. So if you have any kind of questions, please feel free to ask me in class, and we'll see you then.